Thanks for inviting me to speak here, and I'm looking forward to an exciting workshop. It's a pleasure to speak at this workshop. So I'm presenting work that was done actually in collaboration with Micron and as part of the EuroExa project in Europe. I have to admit it's mainly software-focused viewpoint. It's HPC viewpoint, and it's concentrating on memory resources. But I think it's hopefully it's interesting for you guys. Hang on, I haven't. Okay. So a few years ago, we did a study into the memory capacity requirements of HPC applications at BSc. And the figures and the plots that we show here are from the paper that's referenced down there from 2017. So at the top, I mean, the most striking thing that we saw when we were looking at the memory requirements was the dramatic difference in the memory demands per process across these applications. And these are actually important applications that are used. They're from Prace, they're from the UEHAPS suite, and they're used for procurement of the largest HPC systems in Europe. So we see Alia, you can't quite see, but it's 57 megabytes per process, up to some of them being 8 gigabytes, well, maybe six or so gigabytes per process. And part of this is due to the different applications, but it's also due to strong scalability, which is very common in HPC. As you have a fixed problem that you want to solve, and you try to reduce the time to solution by increasing the number of nodes. So quite clearly, as you increase the number of nodes, if the problem size per node is going to drop, that doesn't necessarily mean that the memory demand drops inversely proportionally, but it does tend to drop quite a lot. So here's an example that's sort of in the middle from molecular dynamics, and we see a large decrease as you scale out. So clearly, if you're running applications on a machine like ours, we see a mix of large scale applications, but also a lot of very small ones. So that's another reason why the memory demands vary a lot. And similar pictures have been presented in other keynote talks or in other work. I saw NERSC, they found that 75% of the node hours use less than the 25% of the memory per node, and only about 15% of their workload uses more than 75%. And we did a similar study. I don't think the numbers have been released publicly, that's why I don't quote them, but they're essentially the same story. Another interesting point here is but of course, when you got a new machine or when you want to benchmark it in terms of HPL or HPCG, as you scale the size of the machine, the problem size also scales. This is data from the same paper, which is maybe a few years old now because it's not taking account of new memory technologies, but still the general picture is you need more memory as it gets bigger. But this is an example where the memory demands is basically homogeneous across the machine. The point is, from the previous slide, that in general you have a mix of different applications running at the same time. So I just put this slide in, which just reminds everybody of the machine that we have in Mare Nostrum. This is from 2017 and due to be upgraded soonish, but it's the machine that we're working with that, quite interestingly, is in 4 parts. So we have a general purpose cluster, but we also have some other parts using experimental technology, or maybe not experimental, but different technologies such as ARM Fujitsu. We have an AMD part, and we have a Power 9 part. So in a machine like this, how do we deal with the varying memory demands? And the typical way that's used across HPC is to have a mix of large or sort of normal memory capacity nodes and large memory capacity nodes. So this machine, I think, has 10,000 cores in all, something like that, and 48 cores per node. The large capacity nodes have 8 gigabytes per core, and the normal capacity have 2 gigabytes per core, which actually is pretty much the rule of thumb memory, at least until recently, per core for a machine like that. But it's not very flexible because we only have 2 kinds of memory provisioning. Also, you have to decide ahead of time what proportion of the nodes are going to have the large capacity. In this case, I think it's about 6% of the nodes are high capacity, and it's exposed to the user in that you have to choose one queue. You have to choose the normal queue or the large queue, and maybe most of the time the large queue would have a longer waiting time, but sometimes it's the other way around, of course, depending on the demand that we have in the machine. So pretty much 90% or more of the largest supercomputers in the world, in the top 500 list, have a cluster architecture, which is, of course, the baseline that we are comparing with, which, as we all know, large number of servers interconnected by network. Crucially, of course, each server has its own memory hierarchy and memory capacity that's not used by the processes running on one node, of course, cannot be used by the processes on another node. And of course, we're all here today because this is the kind of thing that we want to go past, this siloing. Of course, if you have large and small memory nodes, which is what we have in Mare Nostrum, then it works quite well when the system that you've provisioned matches the jobs that you submit to the system. So as a motivation, I like this kind of plot, which shows the x-axis is time, the y-axis is utilization from 0 to 100%, and we see memory and CPU. And in this case, where on the left, where the job mix matches the system, then you've been lucky. Doesn't mean that both of them are 100%, but at least one of them should be getting close to 100%. And generally, let's say it's a CPU. CPUs are, on average, maybe about 80% used in HPC, which I think is high compared with cloud, but is one of the characteristics of HPC. But of course, when the job mix doesn't match the system, you're in an unfortunate position where neither of the resources are being fully utilized. So something is clearly going wrong, and it's clearly because of the stranded resources. I must say that these plots are generated from simulation, and I'll explain later in the presentation that the use of simulation is quite important, at least in the work that we've been doing. And of course, as we all know, being here for disaggregated memory or disaggregated and composable architectures, the idea is to share, well, in general, when I said composable, it means sharing not just the memory capacity, but also storage and accelerators, which of course are very important in HPC across the nodes. And in terms of memory, the stranded resources problem, but also the coarse granularity of provisioning in terms of power of 2 sizing and balancing of memory controller channels and so on, which gives you a small number of possible capacities per node that you can make more flexible when you use one of these architectures. So there's 2 broad approaches. One, and the terms for them seem to differ depending on who you're talking to. Approach 1, some say true disaggregated memory, maybe centralized, where you buy your nodes and you buy your memory separately. And the great advantage of this is that you can provision both of them independently, upgrade them independently. If the technology improves at different rates, maybe you can provision them, procure them differently. And so there's been a lot of work in this direction, including HPE's machine and many others, which I won't go into in detail. The other approach is when the memory is attached to the nodes, but you have the ability to borrow unused memory from other nodes. And a big advantage of this is that you have a tight coupling between the CPU and the memory that's close to it. So if you're not using the disaggregated memory features, then the cost is, well, maybe it's not no cost, but it's a smaller cost than if you have to go a larger distance. And this is actually the approach that we've been looking at BSc and in the Euroexa project. So this is a picture of the architecture that we were starting from. We've been at BSc involved in this effort since 2014 or so, with the Euroserver project, and then Exanode and Euroexa, all of which implemented basically support in FPGAs for memory capacity sharing. So basically the local interconnect was the Amber bus, and with a fairly small interface for talking to remote nodes, then you can basically make remote accesses to the memory that belongs to other nodes. And I should have said in an earlier slide that an important characteristic of a lot of these architectures is that you can use ordinary load store operations. And this is true here. In HPC, of course, there's been RDMA, remote DMA for acceleration of things like MPI, which is going in the direction of this with things like InfiniBand, but for DMA transfers. I think the very new thing in the context of HPC is being able to do individual load stores. Okay, in terms of these kind of architectures, remember I said at the beginning that I'm a software guy, so I kind of look at this and I see changes through the whole software stack to support this. So of course, support in the OS, support in the communication libraries to make use of the architecture you have, maybe the file systems. One very, very large topic is the topic of dynamic changes to the resources that are made available to jobs. So in cloud, I think this is much more established, whereas in HPC, all of the systems at the moment, you reserve resources for the job at the beginning of the job, and these resources are fixed. You've got 32 nodes, these nodes, and from the beginning to the end of the job, you use those nodes. So at the moment, there's no real concept of elasticity in HPC systems. It's not supported in the batch scheduler, which is the next topic. But there is a lot of work that I'm also involved in, that BSc is involved in, and other centers too, which is the whole topic of malleability, to be able to make dynamic changes to maybe add nodes to a current job. So it's sort of elasticity. But in this context, it's also important because as memory is freed up, maybe there's some need to migrate memory and avoid memory fragmentation. I'll talk later about some other aspects related to this. Batch scheduler needs a lot of work, hardware abstraction. Another important thing is the isolation amongst applications. So again, it's the co-scheduling of jobs on the same node is very rarely done in HPC. Generally, we think about using lots of nodes, but even when we're not using many nodes, the idea is exclusive access, and the networks tend to be non-blocking, so the interference between the applications is not so very large. But of course, if you're sharing memory amongst nodes, then the there's going to be interference on the memory bandwidth, and the more interference there is, the higher the latency, and this can affect, maybe it affects just one node, but if it's a large job, then with current programming models, this can very quickly cause a slowdown that affects a job on hundreds or more nodes. So this is a very important aspect to deal with, at least from HPC. And then programming models, they have to be generally open. Big question is whether when you have memory at different distances, whether this is made exposed to the application or not. There are different approaches here. But if it is exposed to the application, this is maybe also a difference from cloud, in that the applications in HPC have very long lifetimes. A lot of the applications, basically lifetimes of decades, with considerable domain knowledge embedded in the source code. So it's very difficult to make major changes to the architecture until new architectural features are well established, and also hopefully open and so on. So it's a major effort to adopt new technologies. So this is a kind of negative slide, actually, now that I go through it, but I think it's important stuff. Then user practices need changing, especially if you need to know ahead of time how much memory is needed. I'll talk about this aspect later, actually, in terms of controlling the memory use of applications. Resilience is another important one. We did an interesting study that is cited at the bottom of this slide, looking at the memory errors in Mare Nostrum 4. And over the 2 years of operation, there were 330 something UEs, but they tend to come in bursts. There were 67 bursts, and the lost node hours was manageable. Yeah, so around 40K node hours. But of course, the more applications that are potentially sharing the memory that's on a node, or memory that's in a memory node even, the more this may be an issue. And security, I'm not really an expert on, but it's also something to be aware of. So out of all the different software aspects that need dealing with, we've started by looking at the job scheduler. And the reason for starting here is to get a kind of broad study of what the effect of this support could be when you're running lots of jobs in terms of throughput and user experience. So the most used, as far as I know, job scheduler in HPC is Slurm. So we work with this, and we developed extensions to Slurm to be aware of disaggregated memory. And the only new information that needs to be provided by the user is the job memory demands. In that you need to estimate how much memory is needed, again, related to this static assignment of resources at the beginning of the job. And we looked at different trade-offs using simulation. Now, why did we use simulation? For two reasons. The first is that we did some work also in the EuroEXA project using FPGA systems, but they tend to have very, very high latencies. So that any performance results that you get out of it are not really very, very useful. Also, the system software, at least at the time, was quite immature, or better systems like Power 10 at the time were not yet available. But even if they were available, these kind of experiments you can't really do on a production machine. You can't borrow Mare Nostrum for a few months and try some different experiments if there's an issue, if there's a risk that is going to negatively impact the service delivered to the users. Of course, as things get more mature, then you do it on the production machine. But we were starting at a sort of pretty much from the beginning. So The simulation approach that we use, I think, is a very good one. So you can do all sorts of different kinds of simulation. What we do is use the actual Slurm daemons. So the Slurm control D that actually does the job scheduling decisions is completely unmodified. The Slurm D that has the job of running the jobs, well, this cheats, doesn't run the jobs, and it estimates what the execution time would be. And then there's an extra daemon for controlling it, for reading the trace, and so on. And this is open source from BSC. So one thing, if you're going to be modeling the effect of disaggregated memory in something like this, is you need some kind of model of the performance impact, because of course it's not coming for free. And so we studied a list of applications, and on the x-axis is the interfering remote memory bandwidth. So the more interference there is from another application, the lower the normalized performance. On the y-axis, the different lines correspond to different number of nodes, because the more nodes you have in your MPI job, the more the noise aspect of the bandwidth interference has the chance of being amplified, because you're taking essentially the maximum over the nodes that you have. And so the performance drop, or the effect of this, becomes worse the more nodes you have on the job, which is one of the aspects I mentioned earlier. We have a model, the input is the curve I just showed, and some other things, the total memory bandwidth. Depending on the context of the other applications, you know how much interference there is and how many there are. And essentially this, I won't go through this in detail, but essentially it's modeling what the effect would be of running these workloads on this machine with disaggregated memory, with this policy. I should say, of course, when you use this model, and it's only used by the simulation framework for evaluation. As I said at the beginning, there's no characterization of the application for the user. It's just so that we can see what the effect would be. And we extended the simulator to support this. Maybe I'll go in detail here. And then we generated some synthetic workloads using a well-known model, augmented it with real application data, and tried it on different job configurations. So I said when we looked at the picture of Mare Nostrum that the proportion of large nodes in that system was 6%, and the large nodes were 4 times the capacity. Here, the large nodes have twice the capacity, actually, and we have a range of large nodes that goes over a wider range than this. And we tried different, well, this is basically the characteristic of the jobs that we had from the trace. An interesting thing is when you're sharing memory capacity, ideally, from the policy's point of view, you would want to share capacity over the entire system. But the larger the system, the larger the latency to access this memory is. So rather than try and figure out what that effect would be, we just did a sweep over the size of the groups in which you are doing the disaggregated memory. This is something where new technologies like photonics might make a difference to the trade-off, and we're not really experts in here. So we looked at if you don't have disaggregated memory, then the throughput on the y-axis in this system, depending on maybe I should say from the beginning. So the columns are the number of large nodes you have. The rows are the current demand of the job mix. The blue is without disaggregated memory, and the y-axis is the normalized throughput. So you see in many of these cases, when the memory is not provisioned enough for the non-disaggregated memory case, the throughput drops massively. You also see from this picture that even being able to share memory across pairs of nodes, which were statically defined, we just had even and odd nodes, then we get a very large benefit from the disaggregated memory. I think it's really interesting. If these results are reproduced by other groups, I think it's interesting to see that you don't need to do disaggregated memory across the whole system to get the majority of the benefit. You can do it across pairs of nodes or even up to 16 nodes or so, and get quite some benefit from the running different jobs together. And then we see if it quantifies the impact. So that was interesting. Let me see, what was this? This was as you change the job mix. So if we have the different plots are for different proportions of large jobs, which was defined to be jobs that need more than the memory that's in a single normal node. As you have more of these, of course, the benefit from the disaggregated system becomes much more important. In this case, in the top left, you don't need disaggregated memory. The more realistic ones, we see really quite a large difference, even taking account of the slowdown that we expect in accessing remote memory. And in many cases, the baseline cannot run some of the jobs, so you can't use the baseline at all anyway. You can't run these jobs. You can't run large jobs if you don't have any large nodes in the baseline. When there's sufficient memory, then disaggregated approach matches the case of the baseline when there's plenty enough memory. And in the other cases, there's a benefit when the memory is constrained. So some numbers here. The response time is the queuing time plus the job's runtime. We see this, of course, reduces because you're making more efficient use of the machine, and we also see not a lot of difference between large and normal jobs. So the experience from the user is similar in the two cases. And then coming back to the plot that we had at the beginning, where we saw that neither the CPU nor the memory was being well utilized. Here we have a scatter plot, a slightly different way of showing it. So the matching case, we see the memory utilization is lowish, but the CPU utilization with or without disaggregated memory is good. This is the case where you have enough memory resources, but more than enough. You've over provisioned it in the current way so that memory isn't an issue. If it's over provisioned, then even more the same. But when we start to reduce the amount of memory to take account of this, make use of disaggregated memory's ability to use the stranded resources, we see that the disaggregated memory continues being, at least in our experiments, CPU or CPU and memory constrained, which was not the case for the non-disaggregated memory approach. And I think this slide says what I just said. Scheduling time per job is not a big problem. So one last thing that we started looking at, I think, is really a crucial question, is this assumption that we made at the beginning to say that the user has to specify the memory demands of the job. And we're using the environment that HPC currently has, which is that the resources are assigned statically. The thing is, the previous results assumed that the users were 100% accurate on their memory requirements. So perhaps it's not particularly realistic, given that the incentives are kind of not quite balanced. Because if you estimate your job requirements and it's too low, then sorry, but if you exceed that, then your job is going to be killed. And actually, a lot of these machines don't even have swap configured. So if you go over the memory that you estimate, then it gets killed, which is quite a serious issue. If you estimate a bit on the high side, well, okay, you're going to waste some HPC resources, but at least your job finishes. So this is the question: how important is it? Is there a natural incentive to be honest? But not, I wouldn't say honest. I mean, to be accurate in your estimate, or do we really have to not do this statically? So we looked at the most obvious sweep, of course, is on the x-axis. We take the job mixes that we had before, and we just overestimate the memory requirements of the jobs. 0 is the previous result. I'm sorry about that. 60% is if all the jobs overestimate by 60%. And clearly we see a drop in throughput as you do that. That's not so surprising. The drop is higher the more extreme the kind of reduction in the memory provisioning of the system is, but there's still a drop. And then the question is, what is the user's experience? Because that is the system administrator's experience in a sense of what throughput can we get. So how will my memory estimates affect the job response time of my job? Again, job response time is queuing time plus runtime. We'd like to plot this as a function of this overestimation with everything else constant, which you can't do one job at a time. Of course, we do a correlation analysis. And here we plot all the jobs, response time on the y-axis, memory overestimation there. We've got a lot of different kinds of jobs. In fact, we have a very skewed distribution in terms of job size. The average number of nodes for a job is surprisingly small on Mare Nostrum. But then the largest jobs run on the whole machine. And some of them run for minutes up to days or weeks or so. And of course, when your job runs, anyone who's used these machines knows that sometimes you can get your nodes immediately, and sometimes you have to wait 10 minutes, 20 minutes or so for a small number of nodes. So of course, there's a large range in response time across all of the jobs. So we have to do some kind of filtering on the baseline response time. So this is one range of jobs that are similar. We do the correlation analysis across there, and now we see a clearer trend line. Remembering that this is the overestimation of a single job. Well, it's a correlation, sorry, between jobs that are submitted with random overestimation, correlation between their overestimation and their response time for a range of response times that you, the sort of baseline response times or baseline run times. You get some trend lines. When you bring this together, we can get a picture for how the slope of that trend line changes as a function of the baseline response time for different kinds of users, depending on whether you are accurate in your memory demands or less accurate. And the headline out of all of this, if you compare the red line and the blue line, red line is if you overestimate by 100%. Blue line, which in many cases is immediately below the red line or covered by it, you can't see it apart from a few places, is if you're really accurate. So essentially we concluded that in this setup, if you're not controlling memory use in a separate way, then of course we can't say what the users would actually do. All we can say is there's not really an incentive to be accurate, right? We can rely on the goodwill of users, or we can find a way to solve this, maybe through peer review, maybe through allocating memory as an extra thing as part of the process to get access to the machine, or more likely finding a way to allocate the resources dynamically rather than statically. Again, I said this was a big thing in HPC, but we're not there yet. So anyway, conclusion for the whole talk is, I think from our study that we've done here, this whole subject of composability, which I didn't touch on so much because I was talking about disaggregated memory mainly, shows great promise in HPC. I showed the slide where it was going through the system software, and it's going to require work across the whole system software stack in HPC, but I think it's worth it. We motivated some results using our simulation with SLAM to show that the benefit is likely there, and that's it. I think it's an interesting topic, and I'm looking forward to seeing the rest of the talks in this session and to the panel session, and we have some time for questions.
Thanks a lot, Paul. Thank you very much for this talk. Extremely interesting. So, is there any question from the audience? Oh, I see some hands. Felix, you can unmute yourself and.
Yeah, sure. I just wanted, to wait.
Yeah, no, go for it.
If there are other questions, I actually have a range of questions, but perhaps I first, ask one and then let's see. So you talked about that in a prototype, I think you used FPGAs, but they had quite some added latency to, memory accesses.
Yes.
And so, do you have a feeling, how certain applications would respond to different memory latencies?
So actually, I'm not sure I have a very good plot there. It was, hang on, my machine is misbehaving a little bit. So where's the plot that we had there? Near the beginning with this one. Not sure how useful it is, but let's take a look. So I think it's actually, I'm not sure this is as useful as I thought, but we have a range of different applications. I mean, some, especially the ones with the dense linear algebra, they are compute bound and can tolerate, I think, a lot more latency. But the majority of the applications, as I understand, are quite sensitive to latency, which is why HPCG, I'm not sure if this is the standard version, but the conjugate gradient is starting to be established as a benchmark in HPC because it's more typical of memory bandwidth prone applications. So I'm not sure I can give you a number off the top of my head, but, and this is related to what I'm showing here with the bandwidth. They can be quite sensitive. Having said that, we did with our setup find, I mean, generally the results are showing a benefit even with the latency that we are adding. Does that answer the question, or?
Yeah, I mean, kind of. So what I'm a little bit after is perhaps it's interesting, the one talk we have, I think, in session 2, because they have instrumented the FPGA to artificially increase the latency, up to, let's say, if you want very high values. And, and this is perhaps quite interesting because, I mean, it's more easy to scale bandwidth than to reduce latency, right? You have
absolutely
speed of light as the maximum, and so.
Yes, certainly I can say for the prototypes we had, the latency with FPGA was a big issue.
All right, thank you.
Okay, we have Alan. He had a question. Alan, you can go for it if you want to ask it. Okay. Or I read it for you otherwise.
Yeah, no problem. Thanks, Christian. Yeah, did you monitor any performance impact on jobs that were running on the node that was actually lending some of its memory to another job on another node?
Yes, this was part of the analysis. Yes.
And what did the performance get hit on the job of the lending node?
It did. I'm trying to remember whether it was worse or it was certainly hit on the lending node. It's something we had to be careful with.
Yeah, I guess I'm more on the hardware side, but when I think about it from the hardware perspective, from a processor that's lending that memory, especially if it's lending its own memory, it's consuming its own local memory bandwidth to donate the memory, and it's consuming its I/O bandwidth to push that memory across to the other node. So you're getting a double hit on the lending node, which could be very serious. I think that's a, you know, all of the analysis on the borrowing node is great, but the impact of the lending node is just as important.
It's just as important. Yes, because and I don't have it here, but we did some studies in terms of the bandwidth latency curve, and as you increase the contention on the memory bandwidth, the issue is the latency goes right up.
Yeah,
and it's the latency, of course, that affects the application.
And that's another very good point. Obviously, an FPGA, as you've been saying, is a massive hitter because it's such a slow device, being programmable. But with these very large processors, you know, many hundreds of cores now, or many tens of cores at least, when you borrow from a memory port and you lend it to an I/O port, if those ports are on both sides of the chip, how much latency do you get just moving it across the lending processor from its memory channel to its I/O channel? Or is that insignificant? Obviously, an FPGA is huge, but is it insignificant on a processor lending memory?
I think that's one more for the hardware guys. It's one where I'm interested to hear the answer, actually.
Yeah. I just to close, I think where the hardware needs to go is we need to think more memory centrically. We need to put the memory in the middle and have a local connection for the local processor and the lending port, a fabric port, to lend it to everybody else. And then the node that's lending doesn't see any bandwidth hit or any power hit or any latency. Basically, it's the best of both worlds, but we've got to start drawing our diagrams with the memory in the middle.
Yeah, actually, that makes a lot of sense. And as I said, this is something that really hurts in HPC.
Exactly.
Because of the noise effect. All of the node, or pretty much all of the nodes, could be perfect with no local memory interference. One of them has the interference, and well, there's some other work I'm involved in with load balancing in HPC and more advanced programming models, but most of the applications so far don't adapt in any way to this when it happens.
Right. Yeah. Okay. Thank you. Good presentation. Enjoyed it.
Thanks, Alan. And there was a question from Sudhanva. Sudhanva, go ahead.
Yes, thanks. So good question. In one of your slides, you mentioned that you saw, I think on Mare Nostrum, a burst of errors coming out of memory. I'm just curious, is that a burst of errors at different addresses, or was it something like a stuck-at fault where repeated accesses to it was causing UEs? I'm wondering if you have any characterization on that.
I think the best I can do is point to the paper. If I can find it, I can also put in the chat if you have access to it. That goes into details on the characterization. I think some of them are related to over temperature, for instance. Of course, once you have an over temperature, it tends to you have the you're going to stay in over temperature. I'm trying to think whether I don't have a good answer. My colleague is more of an expert in that aspect.
I can take a look at the.
But this is the paper. Do you want me to put it in the chat so that you have a link?
Sure, yeah, or I'll just get it from the recording.
Or take it from the recording. I'll put it there anyway, if it lets me. Okay. Any other questions?
Christine, you're muted.
Oh, I'm mute again. I was saying yes, there was another question from Charles Jones. Charles, you wanna ask it or read it?
Yes, that's fine. So you showed two different types of composability: memory disaggregation with memory borrowing, and then the full disaggregation. Have you looked at any cases where you have a small amount of local memory and then pooled memory? That way you get rid of any, in the borrowing case, the interference from other CPUs borrowing your memory, and you get a very low latency local memory.
Honestly, we haven't. We assume a model where the local memory is fast, but this is something that I guess we can model in the scheduler without really changing the topology that we are assuming.
Make sure instead of having a flat memory, that's all distant remote memory in your first case, and
So,
you would have more of a NUMA type memory.
So the model that we assume in all the experiments is the one that I'm showing on the slide here. So we're assuming that the local memory is low latency, and you only pay the high latency when you go to a remote memory. It's one thing we can look at in the policy to be more kind of strict about not lending memory on your local node unless you really have to, or even disabling it. But we haven't done the experiments to. It could make a difference.
Okay, thank you.
Thanks for the suggestion.
Thanks, Charles. That's 45. We have one last question from Sergey. Sergey.
Yeah, hi, Paul. Thank you very much. Very interesting talk. A question here about the slurm, right? So you mentioned you did the simulation by changing slurm a little bit. So the question is how hard the slurm is obviously a very popular HPC scheduler. How hard, in your opinion, was it to change slurm to take into account disaggregation or composability, right? Like what would you suggest in changing HPC schedulers to take this new concept into account to schedule jobs properly?
There was a large amount of software engineering work. It took a student, I guess, about a year to get up to speed on, because Slurm is so complex. Even things that you may hope, in terms of the underlying algorithm you're trying to implement, it's very hard to actually make the change in the source code and to test it and so on. I don't have any better answer than that, I'm afraid. Apart from that, it was hard. The other thing I know is that it's the changes that we made. We've released open source, but of course, getting it into the Slurm code base itself is very, very difficult, I understand, because it's used in production in so many systems. I'm not sure that was quite your question, but it just made me think of it.
Yeah, thank you. Like we're going to look into like open source the Slurm changes. We're trying to make it work for, CXL these days, right? And the composable systems, and obviously looking at the HPC schedulers is an interesting topic of making them composable, right? So definitely it's great that you released it, and we would like to maybe touch base with you a little bit at a later stage on that front. So, but anyway, thank you very much. Yeah.
I think the link is in the paper. There's probably, you can probably find fairly easily. If not, drop me an email and I'll send you the link to it.
Thank you.
Thanks, Sergey. And there is very last one. Konstantinos has a question. Konstantinos.
Yeah, it's a follow-up on this. So the Slurm simulator changes, obviously you talked about memory disaggregation, but you can also think in terms of device disaggregation. Does your scheduler handle your simulators, handle that, or that would be extra work involved to consider both memory disaggregation and also being able to grab remote devices and keep them for the duration of the job? Or if you have a workflow that is composed of sub-jobs, have them say for the first and third part of the sub-job, but not for the second and fourth, that type of thing.
So I think the short answer is the policy itself, the changes that we made in Slurm was just for memory. And I think it would be some work to add it for devices as well, because we didn't look at this at all. The simulation approach that we've got, I just put on the slide here, I think you can still use, because it's independent of anything that goes on inside Slurm. For instance, the simulator, we changed it because we had to take account of slowdown estimations, and maybe you want to do that too, I don't know. But apart from that, we didn't change the simulator.
Okay, thank you.